I got weird and I got kicked out of that room, so I was just
Everything.
You're a cute person.
Other than the part where I made Maria move. This presentation is now the highlight of the day. After this is all downhill from me.
That's fair.
Yeah. That's good. This is still a solid highlight.
This is a good solid highlight.
It is a solid highlight. Yeah. Okay. Don't worry about it.
All right.
All right.
Welcome everybody to another installment of our mathematics seminar. We are in full swing. We are continuing to have it every Monday, Wednesday, Friday, so keep showing up if you're enjoying this, and hopefully you are. And if you're not, then whatever, we don't want to hear you. Today we have speaking our own Diana Reichs. So Diana is a local to the Gunnison Valley. She was born in Germany, but she was raised in Crested Butte. And this is actually her second undergraduate degree. Her first degree from Montana State was in global multicultural studies with a minor in German. And so usually we send people from Gunnison to Bozeman, and this time it's worked the other way around. But maybe you'll end up going to graduate school back in Bozeman, I don't know.
We'll see.
So a random fact that you may not know about Diana is that she is 20 Pokemon away, which is very close apparently to a full Pokedex. And today she's going to be telling us about Teigernfaces, which explain to us how to use linear algebra techniques to solve the problem of racial.
Hello, everyone. So, like you said, I'm Diana, and so I started at Western in 2016 in spring, and actually around that time, I happened to find this guy on social media. It's called Big Cat Eric, and then I started following him on YouTube. Let's see, this is what his YouTube page looks like. And so he does this. So his name is Derek, and he does videos about big cats. Hence the name. So he has this webcast series that he does. It's called Walk Around the Compound. And what he does in this series is he just rambles on about whatever he feels like talking about while he walks around the compound, which is a big cat, well, it's an exotic animal sanctuary, but primarily for big cats. It's about an hour and a half northwest of Dallas in Bridgeport, Texas. And so he walks around and just films the cats being cute or angry or whatever while he talks about whatever he feels like talking about. And if you know me, you can probably understand why that I love this kind of stuff. But there is a slight problem. That's that all of these cats look. So to illustrate my point, I'm going to do a test. So, okay, let's hope the volume's up high enough.
Shanti, Naya.
Okay, did you get that? Are you sure?
Shanti, Naya.
All right, one more time, just to be sure.
Shanti, Naya.
Okay.
What is that?
So now here's the test. Right. So who says Shanti? Who says Naya? Mom, you need to vote. All right.
Is it neither?
It's Naya. I'm pretty sure. Pretty sure it's Naya. That's what I got when I was going through the images, trying to figure all that out. Naya seemed like the closest match. but now you see why it's kind of an issue. It's kind of hard to recognize them. So about 1.5 years ago, I had this idea, and I emailed Bob and told him all about it. And he's like, "Yeah, that sounds cool. What if?" Because this was after I had taken the practice course and I learned some about the basics of linear algebra. What if we use some of those techniques to approach this problem? So I chose linear algebra because it has a lot of applications involving matrices, and digital images are pretty easy to represent as matrices because they're just a bunch of rows and columns of numbers that the computer translates into pictures. So you can use them for matrix to manipulate or alter images, rotate, scale, skew them, whatever. And you can also do a lot of comparison. So the technique that I learned about while studying to figure out how to approach this was there's a technique and there's something called an eigenface. So eigenfaces are a set of vectors used in the problem of computer facial recognition for human faces. But in case you didn't know this, tigers also have faces. So the question now is, can we make an eigenface for a tiger or a Teigernface? So what is an eigenface? Well, it's a type of eigenvector. And so eigenfaces kind of map out the distinctive features of a group of faces, and they span the column face of that group of faces. And so because of that, they can efficiently represent that group of faces and tell us a lot of information about that, and we can get into you will get into everything that you can use it for. So here's an example of some eigenfaces. This is from a paper by the 3 people, the first being Miller. I can't remember the second 2 names right now, but you'll see that in the sources. So this is a paper that I based my project off of, and what they did is they used about a set of 600 images and they had 3 images of 200 different people. So these are the eigenfaces that they got from that. First one can kind of, it's like if I looked at somebody, like if I looked at Keenan without my glasses on right now, that's about what it would look like. And then, so after 10 eigenfaces, you get a bit more detail, and it goes on doing more and more detail. These kind of map out like specific features, so you get the most important features in the first ones, and then as it goes on, you don't really have important features, but you get more detail. And you will see when I show you some examples. So this is a group of images that was used in the paper to demonstrate what all you can do. So this first image is of a person that was in the set, and this actual image wasn't also in the set. It's the same guy, but this image right here was not in the set. So this is just an image from outside of that. And then this person was not in the set at all. So no image of her exists in the set, and yeah. So basically what you do to, how you can, so these images over here, this is essentially a weighted sum of the eigenfaces, and those weights, I'll get into how we calculate those weights later on. So you can see it's got a very blurry version up here. You can kind of see more detail here, like the glasses, and then about this point, where it's like 400, where you use 450 of those eigenfaces, you can actually, it's pretty close match. And then say here, you don't get as nice of a match because this woman wasn't in the set, but you can start to see that it is her. You can see those features starting to show up. So the important question is, can we use this on tigers? And the only way to know was to try, so I did, and Yes, you can use it. One thing to note is that the Miller paper had a lot more images than I have because tigers aren't the most cooperative subjects when it comes to photography. So because of that, my training set is fairly limited. There's only 13 tigers, but even so, there are some pretty promising results that you will soon get to see for yourselves. So how do we make an Teigernface? There are a few things that you need to know in order to do this process. You need to know about singular value decomposition, or SVD, and in that, you need to know about singular values because you use those when you do the SVD. You also need to remember how ordering your matrices affects the outcome of matrix multiplication, because as you should remember from your linear algebra courses, matrix multiplication is not commutative. So A times B is not the same as B times A. And then you also need to know about eigenvalues and eigenvectors. So eigenvalues and eigenvectors. So if you recall, a scalar lambda is called an eigenvalue of A if there exists a non-zero vector x in Rn such that Ax equals lambda x. So that vector x is called an eigenvector corresponding to lambda. So you can see this will be an eigenvector of this matrix right here. And this is that's the corresponding eigenvalue. So this matrix times this vector is the same as its eigenvalue times its eigenvector. And so if you did all that multiplication, and you would get the same result either way. So then the singular values. To get the singular values of a matrix X, you take the eigenvalues of X transpose X, and note that all the eigenvalues of X transpose X are going to be positive due to the nature of that X transpose X and what it turns out as. So then you need to make sure they're in a non-increasing order so that if your lambda 1 is the largest value, it's in front, and then it either decreases or it stays the same all the way down. And so our sigma I, those are our singular values, and those are the square roots of those positive eigenvalues of X transpose X. So singular value decomposition. We just went over some of the tools we need to do this. So we want to get the singular value decomposition of a matrix X, which is of size m by n, and the SVD gives us this combination of matrices U, sigma, V transpose. And so where U is of size m by m and it's orthonormal, sigma is m by n and it's a diagonal matrix, and V is n by n and it's orthonormal again. So V, we'll start with that because it gives us what we need to calculate the rest of them. So V is composed of n column vectors, and where those column vectors are the eigenvectors of X transpose X. And one thing to note is that this set of eigenvectors of X transpose X is also a basis of Rn. And then, so then sigma is an n by n matrix, and the diagonal entries of sigma are the singular values of X. And so what we get from that is our rank of X, because the number of non-zero singular values is going to be our rank of X, which is R, which we will be using for V. Well, not for V, but it gives us some helpful information about V. So U, not V, U. So U is, again, a set of column matrices or vectors, and this is calculated by taking those column vectors from V, and you do X times VI, and you normalize it by dividing each of those UIs by 1 over its corresponding singular value. And what's interesting is that this set, U1 to UR, will span the column space of X and is also an orthonormal basis for the column space of X. And that's important because if you recall from linear algebra, the column space of X is the span or the set of all possible linear combinations of its column vectors. So with that column space of X, we can combine those images of our Teigernfaces any way we want. And so we need our set of Teigernfaces to form a basis for the column space of X. So, as I said, U1 to UR is an orthonormal basis for that column space of X. I hope you see where this is going, because those U's are going to be our Teigernfaces. So we need to be doing some SVD stuff here. But there is a problem because while you can directly do these computations, you can have your computer do these computations directly. Mathematica can do it. NumPy, which is a Python library, that can do it. But we're working with a set of 13 images, but those images are 300 by 376 pixels, which means if you represent them as column vectors, you have a matrix that is 112,800 by 13. So trying to make a computer do calculations on a matrix of that size is going to end tragically, very tragically. I've tried it and the computer's just like, no, no. So we need to find some sort of alternative way to do these calculations to get those Teigernfaces. So step one for actually calculating the Teigernfaces is you need to have a group of images and you need to make sure that you have consistent angles, backgrounds, and placement of the Teigernface. So you can't have something like this where you have one that's looking at the camera, then one's just like, what are you doing? One's just being adorable. And these two, I don't know what's going on there. You need them all to be square, facing the camera. These ones, I lined up all the images by the eyes, so the eyes are all in the same place. They all have to be the same size. And you want to try to limit the background if it's not going to be consistent background. So this is the image set that I used. So we have Bonnie, Boomer and Slade are actually brothers, and Jake and Peaser here are also brothers. So we have Bonnie, Boomer, Fire, Jake, Naya, JP or Peaser, Slade, Solano, and then these five, I wasn't able to get their names, so they're Jeff, Jeffrey, Frank, Hank, and MacGyver. So next, we're going to want to get some stuff for the actual calculation. So one thing we need is to kind of distinguish the distinctive feature. We need to separate those distinctive features of each tiger from like each other. So to do this, we get the average, and that's about the same as calculating an average of numbers. You add them all together and divide by 13, and we get this image. So that's what the average tiger looks like, according to our data set. Yes?
So when you say the average, so it's like the way you actually produce this image, you take like each image and like a 13th of the intensity of each pixel or something like that, and then just like
so after getting these images, I translated them into column vectors in Mathematica, and then I added those column vectors together.
Okay, cool.
And divided by the average, or by the number of images. So then, once we have that average, we need to create a matrix of the recentered image vectors minus the average phase, which will give us the distinctive features of each tiger instead of all that overlapping information, because they do all have things in common. So to do that, we have our X, which is where the columns of X are F1 minus A, F2 minus A, so on to F13 minus A. And to kind of normalize it, we use this 1 over the square root of 13. And again, Fn and A are column vectors. So next we need to calculate X transpose X, as I showed you from calculating the SVD. And then from that, we calculate the eigenvectors of that x transpose x, and we get our V matrix. And so now we can get the Teigernfaces, which is our original X matrix, that normalized or that recentered matrix of the images, times our eigenvectors of X transpose X RV, and that gives us Y1, Y2, and so on, where each Yi is a Teigernface. And so here is some of the algebra explaining why we can do that. So basically, this is our shortcut. And that's how we can get those singular vectors from X without having to do an actual SVD. And so here are our Teigernfaces. This is the first one. So you can tell each one kind of gives us slightly different information. You might notice that it's kind of confusing what information that's giving us. That's because the way the computers or the algorithms decide what's important is not what we would decide is important. It's like if we thought, okay, this tiger's got a W on his face with the stripes and this one's got a Y, Fear's not looking at that at all. It's looking at whatever it's deciding to look at. And then, so this is those same Teigernfaces, but with the average face added on. So you can see this is the average plus that first Teigernface, second, and so on. Just to give you an idea of what these would look like as actual tigers. So now that we have all that computation, we can actually start to use it. And so what we can do now is we can find some weighted sums for those images, and we can use those weighted sums to actually reconstruct an image. And then once we get that, so we can do that with all the images in the set, and then we can take an image that's not in that set, like an image of one of those tigers, but like a different image of one of those tigers, and we can compare that sum with the sums of the images in the set to determine the closest match, or we can try to reconstruct that image and see what the subject of that image would look like as a tiger. And then we can also reconstruct an image that's been altered or distorted somehow and see if we can get back the original. So first we're going to look at a reconstruction of Boomer, who's the second tiger in the set. And I mentioned that Boomer and Slade were brothers. They are also at the facility. They are known as the PBs. And there's also a set of brothers there that are known as the BBs, which are a couple of lions. And Big Cat Derek is firmly Team BBs. I am Team TVs because I have to be at this point. And just look how beautiful they are. How can you not love them? So this image is the one that was in the set. So let's look at that reconstruction now. So this is going through. So you have the average face, and this is just using the average face and one of the Teigernfaces. So then we add the second one to that, and then we add the third, fourth, fifth, and so on. And then 13 does something weird. So not entirely sure what that's about, but once we get to 12, we have basically perfect construction of that face. And then, so and you can see, you can get pretty good reconstruction there. And then this next one is actually the same cat, it's another picture of Boomer, but this image was not in the original set. So they are extremely similar, which is why I think we get such good results on this one. There we go. That is Boomer and reconstructed. Okay, so next, let's look at image comparison because we were originally trying to do some facial recognition stuff with this. And so what we need to do is we need to find the coefficients for all of the images in the set, and that's those numbers that give us our weighted sum. So like 20% of the Teigernface 1, 5% of Teigernface 2, and so on. And so then if we want to look at one that's not in the set, we need to find the coefficients of that one, and then we compare those coefficients. So to find those coefficients, we can represent our face F as the sum of the average face plus our tiger faces, which are weighted by these B values. So B1 is corresponded with Y1 and so on. And to do that, we use this formula right here. So each B is calculated by our face minus the average dot our yi over yi dot yi. And that, so to compare these coefficients, we do it, the way I did it was just matching up each of those coefficients. So say that our SI is like the first image in the set, and then our C is the image that we want to compare to the set. So this gives, so these A values here and these B values give us our coefficients. And so to do a comparison, what I did was I summed up all those, the difference of all those coefficients to see how close they are together. So the closer is 0 because the sum of, so if you're looking for differences, the closer they are together, the smaller that difference is going to be. So to sum it all up, basically you want your combination, your sums to be close to 0 if you're hoping for a match. So you can see, so this was using the image of Boomer that was in the set and comparing it. So when you have coefficients minus those same coefficients, it should be 0 because you're like subtracting a number from itself. So as you can see, the sum for Boomer is 0, so that's what we want. And so, and according to this, Boomer is closest to Bonnie, whereas his own brother is somewhere down here, which is interesting, but oh well. So now we can move on to some more applications. You don't have to stick to tigers with this. And I apologize for showing you this ugly, disgusting baby. I'm sorry.
Whoa.
He is cute, but you know, I have to pretend he's not.
Lion shaming.
Yeah, so this is what this baby, I think it's Zubiri. This is what he would look like as a tiger.
Okay.
It's a bit odd looking, so it's a good thing he's a lion. And so now to see which one he most closely resembles, we do that same math, and we get a result that he looks most like Tiger E, which is the one I named MacGyver. And he looks the least like Bonnie. So he does not look like a white tiger, apparently. And so
There we
now
go.
we got some contested on some altered images. See, so this is Slade. This is the image from the set that I altered a bit. And so this is a reconstruction of that image using this sum, these weighted sums of tiger faces. You can see it's did a pretty good job. Because that is definitely Slade. What's interesting about that one is that, so here's the map of coefficients for that altered image, and this is a map of coefficients from an image of Slade that was not in the set. So, strangely enough, he's a closer match to Naya or MacGyver than he is to himself, apparently. But this image that was not in the set has almost the same difference, has almost the same comparison as that altered image that was in the set. So at least it's consistent between tiger set Yeah. Either way, it's still the same tiger, even if it doesn't realize that it's like.
Oh,
I think that could be changed with a larger data set. We'll have to see. So to review, you can use these Teigernface method to do a lot of comparison and facial recognition. You can also do it to reconstruct some images. There are some problems and limitations though, mostly because of the way matrix math works. You need all the images to be the same size, and you also need to account for your angles and your lighting and your position, because if they're not as consistent as possible, it's going to throw off your calculations. Like when I was doing testing, first time I did it, I used a picture of Boomer that had different lighting than the one in set, and it was not nearly as close a match as the one that you ended up seeing here. So, but that's something that I want to look into more in the future, because the paper did talk some about that. And the other things I want to do is to try it with color images, which I did kind of start on, but it ended up being a lot easier to use Mathematica, as much as I love Python. And then I also want to look into the methods they talked about in the paper about how to adjust for the angles and backgrounds and lighting and all that. So here's some of my sources. And I do want to do a big thank you to Derek Cron for helping me. Like all those pictures in that set that you saw, those were all taken by Derek. And he's been very interested in this since I mentioned it to him. And I also want to thank my cousin Alex Lundy, because she actually flew me down to Texas and got me to that sanctuary so that I could take those pictures. And she also has a very cute baby, and she is very awesome, and I love her. And to everyone else, all my professors who've helped me and everyone, I want to do a lot of things. So, questions? Matt, Mark.
How big is your image data set? How many images do you have?
Well, for what you saw, it's just those 13 images. I do have some others that I used for like the comparison and stuff, but it was hard to get these pictures because tigers don't cooperate. I have a lot of pictures of fence, of tigers behind the fence, of tigers doing weird things that wouldn't be helpful for this. But yeah, the ones that you saw in that set, those were the tigers that actually had good facing the camera. But
What did you do to coerce the face of the camera?
I didn't do anything. Derek actually just like he would see a tiger walking down and he would just run to the other side and just like take pictures as the tiger walked towards him. A lot of that.
Nice.
Bob?
When you do the comparisons, I think suggestion would be to put some absolute values on that, or
Yeah.
because you get some false cancellations. I think that would give you some misleading results. And I think we'll see more. If you just put absolute values around those differences, make sure everything's measuring them all positive. So to distinguish a little bit more, I think you don't have scatter plot kind of thing really.
All right.
I hope this like one thing that really jump out at you.
Yeah.
Or
Makes
try
sense.
or even do like vector distance or something like that. But there's a concern about negative and positive canceling out that conflicting information.
Right.
Yeah.
I thought you were reading.
Yeah, I just wanted to comment. I thought it was, when you compared the lion to the tiger, and then sort of same idea when you compared the tiger with the glasses. I thought it was pretty cool, even though the lion sort of didn't look like the tiger amalgamation was really, really weird. The parts of the tiger face the parts of the lion face look like tigers, right? Like the consistent colored nose and the dark circles right at the corner of the eye. Like those features were like really bright and clear in the like Teigen face.
Yeah.
Pretty cool.
Yeah.
And the other sunglasses is just like, no,
Good to know.
Okay.
Did you ever try the SVD on that big thousands by 13 matrix?
I did in the beginning, and it just said no.
I feel like, when you did the subtract off matrix phase, you still had 13 columns in that matrix, right?
Yeah.
And then did you do that yourself, or did you ask Mathematica to do the SVD for you?
Well, so Mathematica tried, I think the way Mathematica tries to calculate it is a bit more complex than what I did.
So you
Because,
just formed that transpose X,
yeah,
and that's 13 by 13, right?
yeah.
And that's pretty manageable. I'm shocked that the example is
Yeah, well, that V1 is fine. It's the U that gets really thrown off because that's a big matrix. When I tried it with NumPy, it wouldn't even try to calculate the eigenvectors
Oh, really?
of that my
You
X
said
matrix.
no.
This is too big. I don't want to do it.
No.
Other questions?
So nobody's tried this? That's just crazy.
Well,
It's super awesome. It's super duper awesome, but it was surprising that it's like, yeah, no one said this before. I just figured this out. Really cool.
well, I didn't actually look to see if other people had figured it out. 'Cause I wanted to try it for myself. I wanted to do it for myself. See,
Nice.
because
Trailblazer.
but from what I understand from talking with Derek, there isn't a whole lot of research done into facial recognition for tigers specifically. And it is something that can be very useful to researchers out in the field because you can't always tell just by looking at them, like I showed you in the beginning.
Did you compare your results to the paper with
Well, I didn't really do a formal comparison for my thing in the paper. I was mostly just looking at what they had. There were things that were consistent, like when I first did it, like the angle, I didn't have as nearly as consistent of angles in my pictures and everything. And there was one example that was used in the paper that I didn't show here, where that second face in their image set, that was the same guy, but it was kind of like this instead of like this. That one was much more difficult for them to reconstruct than the picture of the person who wasn't even in the set. And I found similar issues with my own when I was doing all the testing.
Let's thank Diana again.
Yeah. All right. Do I just look in stream? I wasn't sure if there was, if you wanted to do something with that.
I was feeling like a coworker because I open and close.